Hi everyone, this paper studies the deterministic sparse Fourier transform for continuous signals with a frequency gap. As shown in this figure, the Fourier transform is a powerful mathematical tool that transforms the signal from its time domain into its frequency domain and hence recovers its active frequencies and amplitudes. It has several important real-world applications, including signal processing, pattern recognition, image compression, and so on, and this motivates the massive research on Fourier transform in the computer science community. Typically, there are two types of transforms that receive wide interest. The first one is the discrete Fourier transform for an n-dimensional vector x, and the second is the continuous Fourier transform for a function xt in the time domain. There has been a long history of research aiming at computing the Fourier transform more efficiently. For example, one of the most famous results is the Fast Fourier Transform algorithm that computes the DFT in O(n) log n time. However, it is quite challenging to improve on this bound for general signals. For example, if you aim at a sublinear time algorithm in the number of frequency points n. And therefore, the researchers turned to look at the signals which is actually sparse. As quoted here, in many applications, most of the Fourier coefficients of the signals are small or equal to zero. And based on this observation, we have the following definition for a continuous k-sparse signal, which is actually the sum of k Dirac functions centered at the frequency points fj, and each has a coefficient vj. So in the problem of continuous sparse Fourier recovery, we observed that a signal in the time domain with a time-varying noise, and our goal is to recover both the locations and the amplitudes of the active frequencies. Now let me briefly introduce the previous work. In 2012, Hassanieh et al. Gave the first sublinear time randomized algorithm for DFT, and they have an L2 type bound. So this means that the L2 norm of the error vector is upper bounded by the L2 norm of the actual vector after removing the k active frequencies. And later in 2015, President Song extended this result to the continuous setting as we defined earlier, and they have L infinity L2 bound. So here this L2 is in the sense of the L2 norm of the noise function and the L2 sum of the active frequencies. And then in 2020, Lee and Nakos gave a deterministic algorithm for DFT with L infinity L1 type bound. So here a deterministic algorithm is preferable because it does not rely on the randomness of the algorithm. So it is robust to adversaries and outliers. Noticing that there lacks a deterministic algorithm in the continuous setting, our paper fills in this gap and give a L infinity L1 L2 mixed type bound. So actually our guarantee is the mixture of the guarantee in the 2015 paper and that of the 2020 paper. And now let me introduce our main results. We began with the assumption of our sparse signal. So first we assume that the active frequencies is actually on grid. So this means that the possible set of frequency points is formed by equidistant points from -f to f with a given frequency gap eta, which is shown in the number axis below. And second, we introduced the definition of a seek sine noise. So recall that the observed signal is actually the sum of the actual signal x star t and the time-varying noise gt. So we assume that the maximum of gt squared is actually smaller than c times the L2 mean of gt plus a constant psi. So actually this assumption means that there's no spike in the noise function, which is unavoidable for our deterministic algorithm because we only take samples at a finite points of fixed locations in the time domain. So the error could be prohibitively large if the noise function is having a spike on the one of the locations that we sample. And we show that several function classes actually satisfy this assumption, including all uniform bounded noise and all bi-Lipschitz noise. So this means that this assumption is quite mild for application. And last, let me introduce our main result. So for a sufficiently large time domain T, there exists a deterministic algorithm that observes the signal at time points in a fixed set S with size roughly k squared. So here this S is determined before running the observations and recoveries. And then the algorithm finds an OK sparse vector such that at each frequency point, the noise level is bounded by the L1 mean of the active frequencies and the L2 energy bound of GT. So this is the L1, L2 mixed bound I referred earlier. And last, our algorithm runs in roughly k squared time, which is sublinear in the number of frequency points, which is f over eta. So for more technical details, please come by our poster. And this is our references. Thank you for listening.